Hello, good morning. It's my pleasure to be here at the Fusion Conference to deliver a talk. And my topic today is about megawatt solid-state transformer for AI data centers, enabling on-site generation, storage, and AI-enabled intelligent energy management. So my name is Chris Mee. I'm a distinguished professor at the San Diego State University. I'm also co-founder and CTO of Novus Power Inc. To be clear, there is a lot of hype today in terms of data center development. One of the bottom line is that we need a lot of power to supply the data center demand. Estimate by IEA was that by 2024, we already had 180 trillion watt hour of power consumed by data centers. And that increase is in double digits every year. By 2030, the energy consumption by data centers can ramp up to more than 300 terawatt hour. That huge demand put a lot of pressure on our power grids. And today, our power supply for the data center is realized in a traditional way. We get power from a medium voltage power grid through an iron core transformer, step down that medium voltage, typically between 4,000 to 45,000 volts, to a lower voltage at around 480 volts. We rectify that voltage to a DC, and then we regulate that DC to supply power to the computing racks inside data centers. And this process has been working. However, we do have a few issues. One is the large size and weight of the system. And second is energy efficiency because the multi-stage power conversion of the system. Third, the traditional transformer is a passive device. It does not have the function of voltage regulation or frequency control. It cannot manage the power fluctuations of data centers. So the functionality and control is very limited. There's no redundancy. There's limited controllability. It is incompatible with our modern microgrids. In particular, we're talking about AC grids and on-site generation. So that has led to us to look for new solutions. One of the technology is a solid-state transformer, or SSTs. SST eliminates the need of a traditional low-frequency transformer. And it incorporates a high-frequency isolation transformer to minimize the size, decrease weight, increase efficiency, and increase redundancy. Well, the bottom of the diagram shows the transformer design for our current isolation transformer in SSTs. That impose a number of issues. And just so that we understand, there are multiple companies around the world working on SSTs. US alone, we have more than 20 companies working on SSTs, and everybody is seeing SST as a solution, as also NVIDIA has been suggested in their newest white paper. But the issues with SST, one of the issue is it's expensive. So how to reduce the system cost is a good question to ask for any SST companies. Second, this is probably the most important issue, is a high-frequency transformer design remains largely, it's an issue because it can break down at a high voltage, and it increases the reliability concerns. The existing design platforms cannot conduct optimizations for SSTs, and then not to talk about real-time simulations. The data centers also increasingly rely on solar generation, fuel cells, on-site energy storage, and the SST that has been proposed lacks the multi-port integration capability today. Some of them are, some of them not. The high power density, on the other hand, also exacerbates the thermal cycling problem for data centers, the device stress and the energy loss. And then so finally, really, the SSD cannot handle the dynamics that are imposed on traditional system without some thinking. And the key point for this insulation breakdown, summer failure, and so on, was imposed. And when we talk about data centers, we had this AI Energy Summit in March 2026 in San Diego, and we asked data center operators, and what's your concern? Well, they said the concern on the power supply side is the insulation breakdown, the summer failure, and the high cost. So to address that issue, SDSU, working with Novus Power, we come up with 4 pillars of unique technology that we can address all those issues in this suite of solutions. The solutions we provided are concentrated in 4 aspects. So one is the split air gap transformer, sometimes also called variable air gap transformer, that enhances insulation. Second is a double-sided LCC topology. And the third is AI-assisted design optimization, a digital twin. And the last one is the AI-enabled intelligent energy management system. By doing all these 4 aspects, we're able to address the concerns of any modern data centers right away. Let me explain a little bit detail over the next couple of slides what we have exactly done in terms of 4 pillars of solutions that we provided. This here, I want to explain to you the illustration of how SSD can work with a modern high-power electric vehicle charger station, or the charging hub, where you incorporate the solar generation and energy storage. The SSD can handle the highly dynamic demand of charging stations, and also can reduce the power demand from the grid by using the energy storage and on-site generation. And in this case, you can reduce the peak demand from the grid by likely 20 to 50%, but still being able to meet the charging demand of all vehicles, whether it's megawatt, hundreds of kilowatts, or a slow charging at tens of kilowatts. For data centers, it's even simpler, because we incorporate the SSD to manage the grid, the solar generation, the storage system, and any other on-site generation on a common DC grid, DC microgrid. By doing that, we're able to manage the grid power demand. We can reduce, by doing an intelligent control using our IMS, we can reduce electricity cost for data centers by as much as 25%. And that is very attractive for data centers because power consumption is one of the single largest operating cost for any modern data centers. Inside the SSD, you have on the top of this slide, you can see that we have multiple SSD modules put together. On the primary side, we have SSDs in series to make up the high voltage, the medium voltage in this case, whether it's 4,000 or whether it's 45,000. On the secondary, we have all the SSD modules in parallel to deliver the high DC current. The bottom graph shows exact circuit topology we have developed. It incorporates a double-sided LCC topology and a split winding transformer. The split winding transformer is a design that separates the low voltage and high voltage windings so that we can realize a very high insulation, up to 1,000,000 volt insulation. Typically, you need about 100,000 volt for the insulation. So in this design, we are able to do that. In the meantime, we also have the double-sided LCC topology to form the resonant condition for the switching device so that we can realize softer switching, reduce current on the transformer. By doing this, we can increase the system efficiency by 0.2%. You might say, well, 0.2% is not a lot. Yes, I agree. However, if you're talking about tens or hundreds of megawatt power consumption in data centers, that makes a huge difference. Earlier, I talked about the digital twin and the real-time simulation of SSDs. In this process, we are working to develop highly capable digital twin of SSD that can deliver real-time performance or real-time simulation of a SSD, incorporating with AI enabled or machine learning enabled SSD model that can evolve over time. It also incorporates real-time sensory information of SSDs in the real world, so that this system constantly displays the real-time performance of SSD, and it tells the operator when you need to upgrade your system, maintain your system, or doing some sort of diagnostics, checkup, and so on. So lastly, we have this multi-time control. That is the base for our IMS. We perform the nanotime scale switching control, and we do the milliseconds control to handle the highly dynamic demand of power centers. At the minutes and hours level, we handle the highly dynamic demand. We handle the pricing fluctuations of the grid. And by doing that, we help the data center to save as much as 25% of electricity cost. And lastly, we also have this predictive thermal management system incorporated to handle the highly dynamic power demand, where you can have fluctuations in terms of thermal demand, the thermal or the cooling demand of that system. And by doing this, we can extend the lifetime, increase reliability of data center power supply. In the last few months, we have been able to do a laboratory setup. Over here, you can see the system setup, the primary, the secondary, and also the isolation transformer. By doing that, we did, for example, the testing at the device level with nanoseconds, and you can see the switching waveforms are almost perfect without much of noise in there. I want to also mention that we have not incorporated our optical fiber communication yet. You can already see a good waveform. By doing the future design with optical fiber, you will have a much better waveform as well. This shows the PFC, the front end, the active rectification, and you can see the AC waveform in the middle. The green line is almost a perfect sine waveform. We have a PFC less than 3%, and the requirement was less than 5%. And we might be able to do even 1% THD in the future. The LLC stage in the future will convert into the LCC stage, and you can see the power demand for the system up to 7.7 kilowatt in this diagram, up to 100 kilohertz of switching, and we get a very good efficiency. We were able to reach 32 kilowatt of peak power at the output DC side. We're able to get 98.5% efficiency. In fact, we are incorporating LCC resonant condition and a better switching device. Our target in the next couple of weeks is to reach around 98.9 to 99.1% efficiency for the system. And this is efficiency tested demonstration showing 98% at 8 kilowatts. Our next step is to do a 1.5 megawatt system. We are looking at a number of issues, including electrical clearance, creepage, insulation, airflow, EMI, serviceability, safety, and all that. So after that, design is done, we'll be able to demonstrate a 1.5 megawatt system. We also have an inquiry from another vendor, and they want this 45 kilovolts. In that case, we'll deliver 5 megawatt in one SSD system. So that's what we're doing over the next couple months. And of course, the technology we have developed is not just a certain invention. Actually, it was the 20 years of work inside of wireless power transfer, energy management, and all that working together. For example, this is a demonstration of our work in the energy storage system where we validated the EMS system. And this is another demo system that we have developed. We have been lucky enough to be accepted in the NVIDIA Inception program because of our SSD technology. We also participated in the pitching event as a Warfighting Innovation Summit, where we got the first prize ever. That's the only one winning the final pitch. And we have been working closely with our partners to commercialize our technology. Our company is still in the process of raising venture capital to develop our full-scale SSD. So if anybody's interested, you can contact me. At SDSU, we also have been developing this AI Energy Summit. In 2026, we have organized this event with people from both industry, national labs, academia, sit together to talk about what's the next steps for this design. And we do welcome you to join us next year, March 29th to 30th in San Diego at this AI Energy Summit. At SDSU, we also have a number of other research projects. For example, we've been working with a wireless BMS for energy storage system for electric vehicles. And we've been working with companies and the DOE on wireless charging. And in fact, we have developed this double-sided LCC topology over 15 years ago. And that topology has been written into a number of international standards as a recommended practice for electric vehicle charging. We have designed electrical and hybrid airplane. This is a vertical takeoff and landing airplane platform, and we have designed the propulsion system and the energy storage system for eVTOLs. We have been working on solid-state batteries and also lithium-ion batteries, try to improve the safety and energy density for these batteries within SDSU, within my team. We are also working on cybersecurity as more and more power electronics system incorporated into our modern power grids. Cybersecurity seems to be a more and more important issue, and we have developed the algorithms that are able to handle or mitigate cybersecurity cyber attacks from different perspectives. Right? Our battery management system is something that we've developed for over the past 20 years, and it's been working in multiple commercial systems. And I really, you want to dig out what we have been doing in that area, let me know. With the sponsorship from the California Energy Commission, we've been working with Second Life batteries. We have deployed systems where we can validate the Second Life battery and also validate our IMS system in the past 5-6 years. And this shows our IMS in real time, where you can see the operating condition of each battery and how the system is managing the power demand from each of the sources so that you can reduce demand charge, reduce electricity cost, and in the meantime, maintain a better service life for the energy storage system, batteries. Right? And finally, we're also working with Princeton New Energy to develop a recycling method. In this case, we are doing this plasma-based recycling. We can reduce the power consumption in the recycling process by at least 40% and increase the purity of the material that we recycle from the recycled battery cells. So I want to acknowledge my students and our sponsors for the support and for their hard work. And with that, I want to acknowledge your attendance at this conference, and I want you to thank you for listening to this. And if you have any questions, feel free to contact me. My email is cmi@sdsu.edu. I'm also hiring fully funded postdocs and PhD candidates. Let me know if you are interested. Thank you for listening, and I'll see you next time. Bye-bye.